Hello, everyone. Due to visa issues or personal reasons, the authors of the paper cannot come here, so I will help them to present their paper. Okay, the title of the paper is Learning with Non-Convex Truncated Losses by SGD. As we know, many machine learning tasks can be formulated as a risk minimization problem. Here, we would like to minimize a function which can be written as the expectation of a random function. Capital Z here is a random variable follows from an unknown distribution, and F star is the optimal solution of this problem. However, because of the unknown distribution D, in practice, people usually consider its empirical risk minimization. That is to say, we would like to minimize the following finite sum problem, where n is the sample size. And we use F1 star to denote the optimal solution of this problem, which is also very difficult to be obtained. However, its estimator F tilde usually can be reached in practice. Even if we can get an estimator of the optimal solution, we still would like to know how far it is from the optimal solution in terms of risk minimization problem. So excess risk bound comes out, and it is used to measure the performance of F tilde. With the assumption of bounded losses or Lipschitz continuous, excess risk bounds have been established in many previous work. But this assumption is sometimes too good to be true. So in this paper, we are interested in unbounded losses with heavy-tailed distributions. So what are heavy-tailed distributions? Heavy-tailed distributions are probability distributions whose tails are not exponentially bounded. So their tails are heavier than that of an exponential distribution. So a heavy-tailed distribution tends to have many outliers in its heavy-tailed part. It tends to have many outliers with very large values in its heavy-tailed part. Okay, heavy tail is in fact everywhere. For example, the distribution of wealth or file sizes in computers. But there exist two challenges with heavy-tailed losses. The first is that empirical averages may fail to provide reliable estimates. And the second is that empirical risk minimization may provide large excess risk. So the next question is how to deal with heavy-tailed losses. So a simple idea is to truncate a small part of samples that have heavy-tailed losses. So in this paper, we used some truncation functions, and its definition is given here. So a function phi alpha is a truncation function if it follows the following four conditions. And we also list three examples of truncation functions and plot them with different values of the parameter alpha. It can be seen that with the increasing of parameter alpha, the truncation function will be getting far away from the original loss function. Okay, so instead of learning with the original loss, we learn with the truncated loss in this paper. So you can see here, we truncate the loss function f and use phi alpha f as a new loss function. And f hat is the optimal solution of this new finite sum problem. So, and we are still interested in the excess risk bound of f hat. And to get this bound, we only need to assume that the variance is bounded. Please note that we do not need the loss function itself to be bounded, so it can be heavy-tailed. The proof sketch is quite simple. We just write excess risk bounds into different parts. The black term is non-positive, and the blue terms can be bounded by using the definitions of the truncation function. And the red parts can be bounded by using some concentration inequalities. Okay, so finally we can get the following excess risk bound, and it's on the order of 1 over the square root of n. And this result can be applied to both Lipschitz continuous loss functions and non-Lipschitz continuous loss functions. And I would like to make some remarks on this result. First, for Lipschitz continuous loss functions, Brownlee, Joly, and Lugosi have derived a similar order of excess risk bounds. Their solution is based on minimizing Cartoni's mean estimator, while our solution is empirical minimizer of the truncated losses. Second, for non-Lipschitz continuous loss functions, sorry, I forgot how to pronounce it. Aldebert and Cartini obtained a better excess risk bound, but their results focus on a linear model with square loss, while our excess risk bound is not restricted to linear model and square loss, and is applicable to nonlinear models and non-square loss functions. Okay, so in practice, the empirical minimizers F hat might not be obtained due to the non-convexity of this minimization problem. But we can still get a solution by applying some iterative algorithms such as stochastic gradient descent. So in this paper, we want to provide a direct analysis of SGD for solving the minimization problem in equation 3 to show that truncation has a clear advantage for reducing statistical error. But it would be difficult to analyze SGD for a general problem in equation 3, so we consider a special case. In this paper, we consider a statistic linear model. Here, epsilon I is an error, and we would like to minimize truncated square loss functions. And the update of SGD for minimizing this problem is given here. Okay, so for theoretical results, we can get the following statistical error bound. It is on the order of the square of d log d over n. And W star here is the optimal model, and W alpha is the output of SGD. Okay, the proof builds on some results established by law, but we focus on how truncation helps reduce the statistical error, which is missing in many robust statistics literature. And I would also like to mention that the above result is stronger than previous results on heavy-tailed noise, especially with large noise. Okay, so finally, this paper also provided some empirical results to verify the proposed algorithm. It considered linear regression and used square loss functions with soft truncation functions. It also considered some empirical results about absolute loss functions with soft truncation loss functions. So the first empirical result is about symmetric data. So we considered 4 different kinds of noise, such as student T error, Pareto error, cropped input, and cropped output. And the y-axis is test error. It's mean square error. And the x-axis is noise level. The result shows that the performance of learning with truncation are better than learning without truncation. Okay, so the next empirical results is about a real-world application on cell forecasts. So we use a deeper network model, and it's a nonlinear model. And the result again demonstrates that learning with truncation has a significant improvement over learning without truncation. Okay, so the conclusions. In this paper, we have considered non-convex learning with truncated losses from various perspectives. We have established excess risk bounds for empirical risk minimization based on truncated losses for heavy-tailed output. And we have provided statistical error of an approximate stationary point found by SGD method. Okay, thank you very much. If you have any questions, please contact the authors. Thank you.